Okay, so what I'm going to do is switch over control to your computer right now.
All right.
Okay, great.
Share my desktop.
Exactly.
Now, can you see it?
Yeah, I can see it. Just go full screen with your slides. Great. So whenever you're ready, take it away in about 15 minutes.
All right, I'll start it right now.
Great, thanks.
Okay. Hi, my name is Sang-Hee Lee. I'm from the University of Miami at CMS and NOAA. Title of this talk is there an optimal ENSO pattern that enhances large-scale atmospheric processes conducive to tornado outbreaks in the United States? And Bob Atlas, David Enfield, and Chun-Sai Wang, and Hai-Long Liu are the co-investigator. And then this is the outline of this talk. So what I'm showing you here in the left panel is a F5 tornado that spawned in the April 27 in 2011 in the small city in Tuscaloosa, in Alabama. And what you see here is what happened to the city 2 days afterward. And about the half of the city was destroyed after this event. And so that in the April and May of 2011, we had a record-breaking number of more than 1,000 tornadoes and more than 500 tornado-related fatalities in the United States. And 2011 was one of the 4 deadliest tornado years in the U.S. history, along with 1925 and 1936 and 1917. So many questions were raised as to whether this extreme event in the 2011 has anything to do with long-term climate variability, including the climate change and the global warming. So if you take a look at this number of total U.S. tornadoes during the most active tornado months of April and May, you can see that this the number of tornadoes has been increased since 1950. It's almost tripled during this 6-year period. However, we have to be very careful with this tornado database because this tornado data set has many problems, especially in the earlier period before 1990. So that if you actually remove this F0 tornado from this database, so F0 means very weak tornadoes, this positive trend actually disappears, as you can see in the middle panel. So that this positive trend of the tornado database here is probably due to the problems in the tornado database and not really physical. So what we did in this study is that we just used this number of intense U.S. tornado data set, F3 to F5 in the April and May, as our primary tornado index, because we think that the intense and long-lived tornadoes are much more likely to be detected and reported even before a national network of the Doppler radar was built in 1990. And this is our tornado index that we used here. And then we also use other indexes, such as intense tornado days. All right, so this schematic picture illustrates why we have a very high tornado activities in the U.S. So in the central U.S. east of the Rockies, we have this cold and dry upper-level air coming from the high latitude that converges with the warm and moist low-level air coming from the Gulf of Mexico. And when these two different air masses collide in a different altitude, this large-scale differential advection. And because of this increased large-scale differential advection, we have this conditionally unstable atmosphere with a very high cape is formed here. And also because the wind direction change with altitude, there is also a very strong windy shear in the low level associated with it. And those conditions provide a favorable environment to form an intense rotating thunderstorm known as supercell. All right, so Next thing, the first thing we tried was that we just trying to try this linear correlation between the tornado activity and the various climate indices. For instance, this moisture transport from Gulf of Mexico to U.S., it is highly correlated with the tornado activity. And the low-level windy shear, vertical windy shear east of the Rocky is also strongly and significantly correlated with the tornado activity. However, if you look at all these climate indices below this point, it's a pretty none of these climate indices are strongly correlated with the tornado. For instance, if you look at Niño 3.4, that is sea surface temperature anomaly in the central and the eastern tropical Pacific. The correlation is very, very small, 0.11, and that is consistent with the previous studies. But the interesting thing is that it's negatively correlated, so which means that tornado activity is increased during La Nina, and it is decreased during the El Nino. So of course, this correlation is very small, of course. And if you look at the Niño 4, that is a little toward the west, so in the central tropical Pacific, the correlation is slightly increased, but still insignificant, and it's still negative. And if you go farther to the far eastern tropical Pacific in Niño 1+2 region, then this correlation is still weak. But interesting thing is that it's now positively correlated. So, so the next thing we tried was this index, a Trans-Niño index. So you can see that this correlation between the Trans-Niño index and the tornado activity is pretty high, and it's significant. In fact, this Trans-Niño is actually a combination of Niño 1+2 and Niño 4. It's basically a combination of these two indexes. I'm going to talk about it in the next slide. But in any case, all this this table suggests that the U.S. tornado activity is more strongly correlated with so-called Trans-Niño index than any other climate pattern that you see below this point. Okay. All right. So what is this Trans-Niño? So Trans-Niño is defined as the difference in normalized sea surface temperature anomalies between the Niño 1+2 in the far eastern tropical Pacific and the Niño 4 in the central tropical Pacific. That was suggested by Trambert and Stefaniak in 2001. So if you look at it carefully, then the Trans-Niño is basically a zonal gradient of the SST along the tropical Pacific. So in this configuration, when we have a warm anomaly in the east and the cold anomaly in the central tropical Pacific, then the zonal gradient here is positive, right? So we call it positive phase Trans-Niño. If the situation is opposite, for instance, if we have a cold anomaly here and warm anomaly here, then the zonal gradient is negative. Then we call it negative phase Trans-Niño. Basically, Trans-Niño represent the Trans-Niño is not really independent from ENSO because it really represents the evolution of the ENSO during its onset and the decay phases, which frequently occurs in boreal spring, which is also a tornado season. So if you look at the spatial structure of the Trans-Niño here, it's very different from the canonical El Nino pattern, canonical El Nino and La Nina pattern that we see in the bottom panel. So the question is, why is the number of the intense U.S. tornado significantly correlated with the Trans-Niño, but not with the conventional ENSO? That's the question that we addressed in the next slide. However, I have to point out that the correlation analysis table that I showed you earlier could be misleading, because if we go back and take a look at the tornado time series, if you look at the characteristics of this time series, it's really far away from Gaussian distribution. So if your time series is not Gaussian distribution, then this linear correlation analysis could be misleading. Okay. So basically, so what happened here is that we see this smaller fluctuation of the tornado activity. On top of it, we have this large outliers years, this outlier years, and in this case, we can call it outbreak years. For this study, we are really interested in this outbreak years rather than the small scale fluctuation. So what we did next was back to my so what we did next was that we just look at this top 10 extreme tornado outbreak years and between 1950 to 2010, and they are all listed in this table. So number 1 was 1974, number 2, 1965, so on and so forth, all the way to number 9, that is 2008, which was also outbreak years, and then 1998. So you can see, oops, sorry about that. So if you look at this table, many of these years are positive Trans-Niño years, as you can see in this column. In fact, the 7 of this 10 years are positive phase Trans-Niño years, and including this top 3. Okay, so next question is, so what are these key atmospheric conditions that are conducive to tornado outbreaks in the United States? So what I'm showing you here in the left panels are all these atmospheric conditions during the 10 most active tornado years. And what I'm showing you here in the right panels are the atmospheric conditions during the 10 least active tornado years. So as you can see here in the first panel, now this is the geopotential height and wind at 500 millibar. You can see this anomalous upper-level cyclones over the North America. Oh, by the way, this whole thing here is our anomalies from the climatology, not the total. So you can see that there is this cyclone anomaly bring more cold and dry air, upper-level air, to the east of the Rockies. And you can see this increased moisture transport from the Gulf of Mexico to the U.S., and also increased low-level wind shear east of the Rockies. And these 3 atmospheric conditions, I'm going to call it as large-scale differential advection. Yeah, and then I think I skipped one slide here somewhere. Yeah, oh, I did it. No, I'm sorry. Yeah, and then if you look at this right panels here, those are the exactly opposite to what you see during these most active years. Basically, the cold air advection in the upper level is decreased, and the moisture transport is also decreased, and the vertical wind shear in the low level also decreases. So this picture shows very clear atmospheric condition conducive for U.S. tornado outbreaks. Okay, so what I'm showing you here is basically the same 3 plots, same atmospheric condition as the previous slide, but this is for the 10 strong positive Trans-Niño years. So it's a composite of those 10 years. You can see this anomalous upper-level cyclones over the North America that bring more cold and dry air, upper-level air to the east of the Rockies, and increased moisture transport, and also increased low-level wind shear. All 3 conditions are consistent with the atmospheric condition that you expect from the atmospheric condition of this top 10 extreme tornado outbreak years. Okay, I have one more evidence. It shows what I'm showing you here is there's all the incidents of the intense tornado, F3 and F5 tornado, during the 10 positive Trans-Niño years, 10 neutral Trans-Niño years, and 10 negative Trans-Niño years. So you can see that this number of the intense tornado is increased from here, 168 during the 10 neutral Trans-Niño years, to 304 during the 10 positive Trans-Niño years. So it's almost double. By the way, this green is for F3 case, F4 is for the blue, and F5 is for the red. Okay. So, okay, I have 3 more slides. Okay, so if you look at this historical U.S. tornado outbreak years, such as 1925, 1974, and 2011, and also 1936 and 1917, all those historical U.S. tornado outbreak years, you can see that they are all under a positive phase of Trans-Niño years. Trans-Niño, those things are really characterized by the positive phase of Trans-Niño in the tropical. And if you look at the atmospheric condition during the outbreak years of 2011 and 1974, you can see that all 3 conditions, this upper level anomalies, moisture transport, and vertical wind shear, all 3 conditions in 2011 and 1974 are all consistent with atmospheric condition during these 10 positive Trans-Niño years. I'm almost done. So here's a summary and discussion. So the observations and the reanalysis product are used to show that a positive phase of the Trans-Niño is linked to the U.S. tornado outbreaks. And the link between the Trans-Niño and the U.S. tornado outbreak is due to this enhanced so-called larger scale differential advection during a positive phase of Trans-Niño. And during this, when this larger scale differential advection is enhanced, then we have these 3 distinctive patterns in the atmosphere that are conducive to tornado outbreaks in the United States. And then the last thing that I'd like to mention is that we have this new paper coming out in press in the Journal Climate. It will come out this month or so. Here in this paper, we talk more about the mechanism of the Trans-Niño and U.S. tornado activity. I will end it here. Thank you very much.
Great. Thanks a lot, Sankey. We have time for 1 or 2 questions. Does anybody in the room here have a question for Sankey?
Yeah. Hi, Sankey. This is Anarita.
Hi.
Hi. I was just wondering, in terms of predictability of the Trans-Niño index, how does it compare with the, I don't know, the more traditional ENSO indices that you looked at that?
Well, actually, I haven't looked at it carefully, but I can show you this plot here. I have extra plot right here. Actually, basically, this in your positive phase of Trans-Niño is actually, what I'm showing you here is actually the tropical Pacific temperature anomaly between 5 degrees south to 5 degrees north, from west to the east, from January of the developing ENSO year to the December of the decaying year. So this is a composite of all the La Niñas between 1950 and 1978. You can see that this positive Trans-Niño pattern occur when this La Niña is decaying. And also, you can see this positive phase of Trans-Niño when the El Niño is developing. But it looks like this after this climate shift in 1976 and 77, this, during the El Niño onset season, we don't see this Trans-Niño any longer. But during the decay phase of life, we still. Okay, that's it.
Okay, great. Are there any questions on the phone line?
Yes, I have one. This is Ryan calling from NC State. I wonder if you could briefly summarize the mechanism causing this correlation.
Oh, that is basically Trans-Niño. What happened is that Trans-Niño, when we have a positive phase of Trans-Niño, we have a cold SST anomaly in the central tropical Pacific. That induced a stationary Rossby wave that looks like a PNA pattern, a negative phase of PNA pattern, and that stationary Rossby wave pattern is responsible for it. And then we have done some more model experiments to explore further in that issue. So those things are really or included in the paper, which is actually available online. Thank you.
Okay, great. So thanks very much, Sang-Hee. I think we need to move along to the next speaker, who is Rong-Fu. Rong, are you on the line?
Yes. Can you hear me?
I can. Great. So what I'm going to try to do is switch control over to your computer.
Mm-hmm. First of all, I'm very glad.
I'm sorry, Rong?
Can you hear me? I hear very strong echo.
Yes, I can hear you.
Okay. I'm very glad to have this opportunity to.
Rong, sorry, hold on a sec. We can't see your slides yet. What you need to do is click the Quick Start tab in the WebEx window, and then click the right.
Okay, let me Quick Start tab.
What program are you in right now, like on your computer?
I used to have a big window, but now I don't have it anymore. I have a Cisco.
You're in Cisco? Do you have a menu at the top of your screen that says Share?
Let's see. Quick Start, Share, okay. Connected. Sorry, I don't see Share. Is that on the top left?
Yeah, it should be one of the menus on the top of your screen, but you may not be in the meeting center right now. You might be in your web browser or in PowerPoint. So what you want to do is get out of, switch from those applications over to the meeting center application.
Okay. And I have a Quick Start recording.
Great. Okay. Click the Quick Start tab and then click the Share My Desktop button.
Oh, okay. Yes.
Great.
Okay.
Okay.
You're able to see my
desktop? We can see it. Yeah. So go to your slides, go full screen, and take it away.
Okay. Is it working now?
Yeah. Yeah, but you should click in your PowerPoint. Go full screen in your PowerPoint, and then, yep, okay, take it away, you're good.
Okay, great. Yeah, thanks, sorry about that.
No problem.
Yep. In this talk, I'm going to report our result of evaluation of the CMAP-5 model, and also discuss their implication to climate projection for the South Central United States. And the results are included in a manuscript submitted to Journal of Climate Special Issue, which is led and sponsored by the MAPP CMAP-5 task force. Now we're revising this manuscript. And we know that from 2011 and 2012 drought is one of the most costly natural disaster. And as we can see, oh, my screen is moving forward. Sorry about that. So into the future, as shown by, illustrated by the water mitigation policy developed by Texas Water Development Board, the drought is going to be even more costly. For example, the drought of 1950s, if it occurred in 2060, it would be cost more than 100 billion for the Texas. And the cost of mitigation is also very high. And for Texas alone, it could be 50 billion. So in this case, the reliable climate information is very important for state water management to convince state legislator and the voter that their plan is based on sound climate information, especially in terms of future drought. So, however, if we look at the CMAP-5 model climate projection, as shown by this diagram, which shows the projected change of precipitation and evapotranspiration and P minus E over the 5 states in the South Central U.S. And you can see that the projection is, there's a large intermodal discrepancy among different models. With this kind of projection, it's very difficult for water resource managers to convince the legislation to increase budget to put infrastructure, to pay for the infrastructure. So how can we reduce the certainty of this climate projection? And one of the very common approach is through multimodal ensemble projection. And there are many studies in literature have shown that often the multimodal ensemble mean outperform the best quality model. However, in some regions, such as the South Central United States, the model tend to have a similar biases. So in this case, it remains unclear whether multimodal ensemble projection would necessarily reduce the uncertainty. And so in this study, we explore an alternative approach, which is a processes-based model evaluation. And then by removing the less critical model, we would like to see whether the ensemble projection would be different from all model ensemble projection. And there are the metrics we choose in this processes-based model evaluation are based on 3 guidelines. First of all, it has to be relevant to climate projection. And most of the previous model evaluation has been focused on seasonal interannual variation, and these are very important. However, these evaluations do not necessarily tell us how well model model could respond to external forcing, especially the anthropogenic forcing. And therefore, it is important to evaluate whether these regional climate change respond to global warming or global SST warming in a realistic way. So the second is it has to capture the processes that control drought or extreme events over the South Central U.S. For example, in the last webinar, we have showed our observational analysis and basically identify the cumulative surface water deficit, soil moisture, as a very important condition for a precursor for extreme drought. And also, for example, 500 hectopascal middle tropospheric anthracite ridge during the summer is also very important for drought. And finally, the connection between regional rainfall and the ENSO are very important. So the evaluation need to look at whether model could adequately capture these key processes for the extreme events. And finally, the variable we choose has to be comparable to long-term observation, which basically are surface meteorological condition and reanalysis. And so this slide, in this slide, we list the data we used as well as the model we used. And the number in the parentheses indicate the number of ensemble simulation, historical simulation available for each model. What we do is we average over all ensemble members, and so each model have one ensemble mean. And we also remap all the model and data to 2.5-degree spatial resolution. So the analysis period is for the meteorological data we use about from 50 to 205. When we try look at when we trying to identify the global SST warming mode, follow Schubert et al. 208, we use the period of 1900 to 205. And then the surface energy water balance, because we use the NLDES, so the period is 1980 to 205. This slide shows the comparison between observation and the model for the seasonal cycle of daily maximum temperature. and the daily minimum temperature, surface humidity, surface air humidity, precipitation, evapotranspiration, and the P minus ET over the south central U.S. domain. The thick black line represents the observation, and the thick red line represents the multi-model ensemble mean. And as we can see that most of the model underestimate surface maximum temperature and overestimate rainfall, especially during spring and summer. And the model also overestimate ET, and however, as a net result of these overestimation of both precipitation and ET, the model actually has a dry bias in summer. In this slide, we compare of PDF of the daily maximum minimum temperature and P precipitation and P minus ET with observation. Again, as you can see that the model tend to overestimate occurrence of cooler surface maximum temperature and underestimate warm daily maximum. However, the model also tend to underestimate the extreme daily maximum temperature. And the model overall overestimate the warm daily minimum temperature, underestimate the daily cooler minimum temperature. This is consistent with wet bias showed in the previous slide. And the model, as we all know, that model underestimate the extreme rain rate as well as non-raining day, and slightly overestimate the medium rainfall. And so the panel to the left compares the observed P minus ET with the modeled P minus ET, and the bold red curve represent the multi-model ensemble mean. And as you can see that these models tend to underestimate the extreme anomalies of a P minus ET, both on the dry side as well as on the wet side. So how well model could represent the spatial pattern of the extreme temperature? And this figures compares the observed occurrence of the daily maximum temperature, that is warmer than 90 degrees Fahrenheit, and to the modeled frequency of occurrence of the extreme temperature. So as you can see that very few models could capture the observed spatial pattern as well as the frequency of the extreme temperature. Most models tend to overestimate the extreme temperature over the southeastern Great Plain, whereas observation shows the warmest temperature tend to occur over the west. And so this slide shows the comparison between model and observation for the atmospheric circulation. And this is a standard Taylor diagram. On top of that, we add the root mean square arrow. And as you can see that for 500 hectopascal geopotential, most models doing very well during the winter months, DJF, whereas if you look at the summer, the model is really, the disagreement with observation is much larger compared to winter months. And when we evaluate the spatial pattern, we found this is mainly because most models could not reproduce the middle tropospheric ridge, and this is one reason model produce wet bias. And also models tend to underestimate the westerly wind anomalies in the lower troposphere. And this further contributes to white bias. And how well model could capture the relationship between regional rainfall anomalies and ENSO. And this, in this diagram, we compare these correlation between modeled rainfall anomalies and the Niño-4 and the Niño-3 index. And to the left most column represent observation. So you can see that the observation shows significant correlation only in winter between rainfall over south central U.S. and the Niño. And whereas the model tend to exaggerate this connection during spring, summer, even fall season. And also we evaluate the teleconnection pattern, and very few models could capture adequately this teleconnection pattern. And finally, we look at whether the model could capture the response of the what model could capture the rainfall changing associated with the global warming mode. And in this panel, the dashed line shows the observed precipitation, and the dark black line shows the 10-year running mean of these observed rainfall. And the blue line shows the rainfall change associated with the global SST warming mode. And this global SST warming mode is obtained from rotated EOF, follow the method of Schubert et al. And so basically you can see an increase of rainfall associated with global SST warming mode over the south central U.S. as shown by the blue line. And the red line shows the multi-model ensemble mean rainfall, basically representing the rainfall response to the external forcing, and you do not really see the trend. And when we look at correlation between the south central U.S. summer rainfall and this global SST warming mode for individual model, and you can see most of the model actually give you the wrong sign in terms of the correlation with global warming mode, except for the CCSM4. So bottom line is most of the model cannot adequately capture the relationship between the regional rainfall and interannual variation, the ENSO as well as the global warming SST. How does model quality influence climate projection? And this figure shows the projected change of the daily maximum temperature for the RCP 4.5 scenario at the top and RCP 8.5 scenario at the bottom. And as first of all, almost all the models project a disproportionately strong increase of a warmer daily maximum temperature. And if you look more carefully, that these outlying poor quality models tend to project much stronger increase of warm extreme temperature. So when we compare the multi-model ensemble mean, that include all the climate model to those with removal of a poor quality model, you find that the projected increase of extreme warmer temperature is not as strong when we remove the poor quality model as if we use all the model for ensemble projection. And this figure shows comparison between the projected change of precipitation, ET, and the P minus ET for all 9 models versus the better quality model for the south central U.S. So on the first of all, you can see that most of the outliers are removed when you remove those less reliable model, quality model. Second of all, the ensemble mean of these so-called better performing model, which is represented by red line, suggests a stronger decrease of a P-E or stronger drying during the winter and the spring relative to old model mean, which is the green thick line. And so the removal of a poor performing model does seem to have impact on projection. So I will summarize these results now. And first of all, among the 9 CMIP-5 models we evaluate share common wet and cold bias, mainly due to underestimate of middle tropospheric ridge in summer, and they also underestimate the westerly low-level wind in spring, and that contribute to wet bias. Most of the models cannot adequately capture the variation of the southeast U.S. rainfall associated with ENSO and the increase of the global sea surface temperature. A model consistently project a disproportionately large increase of extreme warm temperature, and as well as minimum temperature. I didn't have time to show here, and the decrease of P-ET in all seasons except for summer. And the less reliable model tend to be outlier in climate projection for south central U.S. region. Removal of these less reliable models tend to give you a weaker increase of extreme warmer surface temperature, but a stronger projected drying in winter and the spring. And finally, I think communicating these models' weakness and capability is important for supporting water resource planning. Thank you.
Great, thanks a lot, Rong. Are there any questions here in the room for Rong?
Ron, what aspects of the CCSM4 do you think created that increased scale or correlation between the SST anomalies and the observed precipitation? Is there a particular parameterization or resolution issue that's not in the other 10 models?
The short answer is we don't know yet, but I think the model is quite sensitive to the east or west SST gradient over the Pacific. And so that's the area. And also CCSM4 tend to give well, actually, last slide I can show you here. The CCSM4 tend to give a more realistic global warming SST mode. The spatial pattern of the CCSM4 for global warming pattern is among the most realistic ones. And when you compare with other models, they cannot really capture adequately the spatial pattern of the global warming mode. And I think that might be one of the reasons that CCSM4 is able to capture the sign of the relationship between rainfall over south central U.S. and the global warming mode.
Are there any questions on the phone line? Okay, well, thanks a lot, Ron. The next speaker is Grant Brandstater. Grant, are you on the line?
Yes, I am.
Okay, great. So what we're going to do for this one is I'm going to show the slides from my computer. So everybody bear with me for a moment while I take back control of the webinar. Hey, Grant, so I have the slides up on my screen. We're on your title slide right now, so whenever you're ready, feel free to go ahead and just, let me know when you want me to switch the slide.
Okay. So I wanted to talk to you today about some work that we've done that has to do with how Rossby wave trains can affect conditions over mid-latitudes, in particular over the United States. And of course, this is an idea that is familiar to everyone because of the role that such wave trains have in ENSO and the role and they provide the mechanism by which a connection is made between what's going on in the tropics and what's going on in mid-latitudes. So today I want to take a little different approach on this, and rather than consider quasi-stationary wave trains, which is the situation for ENSO. In fact, instead I want to consider transient wave trains whose variability takes place on, say, interseasonal timescales. So on the second slide, I've just have a brief outline for the points I want to make. In fact, I'm going to cover two topics. The first is a simple brief analysis just to demonstrate how transient wave trains can in fact influence U.S. conditions. In particular, I'm going to show an example of how they influence the likelihood of having extreme conditions over the U.S. And then the second topic, which is the main topic of the talk, will be addressing a particular mechanism which can induce such wave trains, namely transient tropical rainfall events. So on the next slide, this is just one of two slides that are presenting this example of how transient wave trains can affect U.S. conditions. This is an example from summer, and this is work I'm doing with Haiyan Tang. And here we've just designed an index that of extreme heat waves, and the left panel on this diagram is just simply looking at temperature anomalies over the U.S. during days that qualify by our index as being days when a heat wave has occurred. And so I think this is not a big surprise. We find that if you look at an average heat wave event, it's concentrated over the Great Plains. So this is where most of the heat waves occur when one uses our index. But the problem is that during the 65 years of data that we've looked at, there are only 49 events or 49 days that qualify by our definition as being heat wave days. And so that's not a lot of examples to analyze. And so we've instead turned to a general circulation model in which we have 12,000 years of integration, and we've applied our same index. And the right panel shows the average distribution of temperature anomalies during the heat waves in this model. There are more than 16,000 such days, so now we have very good statistics. And although the heat waves are somewhat stronger in the model, you can see they're occurring at about the same place. So we think it's valid to consider heat waves in this setting. Now the next diagram shows what the circulation looks like during heat wave days. This is the contours on this plot have to do with stream function at 300 millibars, and the middle panel are the circulation anomalies during heat wave days. And so you can see there is a wave train starting in the central North Pacific going across North America, and there's a very strong high right over the location where heat waves generally occur. So you can see how the circulation anomaly is probably helping to induce that heat wave. But from our standpoint, what's especially interesting, if you look at the top and bottom panels, which have to do with what the circulation looks like 5 days before and 5 days after the heat wave, before and after a heat wave. And what we think is interesting is that the structure of the anomaly of this wave train is very different as before and after. And so you can see that before the event, there's a lot more amplitude upstream in in the western part of the North Pacific. After the event, there's a strong amplitude downstream over the North Atlantic, and so this is definitely a transient Rossby wave event, which is responsible for making the heat waves likely to happen. So this is just by way of motivation for why we are interested in these transient heat waves. Now, if we move to the next diagram, this is setting the stage for the remainder of the talk, in which we're looking at one mechanism which can induce these heat waves. Now we're going to move to northern winter conditions, and we're hypothesizing that just as in the ENSO event, situation, that for these transient events, at least sometimes they might be induced by tropical rainfall anomalies. And so this diagram is just reminding you that there are transient rainfall events are very prevalent. This is a Hofmiller diagram of OLR near the equator in the Indian and Pacific Oceans. And so you see not only large envelopes having to do with MJO events, so these are, unfortunately I can't point to one because of the technical problems, but I think many of you are familiar with being able to see an MJO event on this kind of diagram, and it has to do with rainfall anomalies that are propagating towards the east at about 5 degrees of longitude per day. But there are also other envelopes of rainfall which are moving at much faster rates. For example, near the bottom, as indicated by the orange arrow, there's a moist Kelvin wave moving at maybe 12 degrees per day. Near the top, there's a mixed Rossby gravity wave event moving towards the west at about 8 degrees per day. So there are these coherent rainfall events in the tropics which have the potential to produce transient responses in mid-latitudes. And so if one looks at linear theory on the next slide and asks the linearized barotropic vorticity equation, can moving forcing anomalies on the equator affect mid-latitudes, we find the answer is yes. And so what this diagram is showing is how this linear model responds to a source on the equator in 3 different situations. The top panel has to do with the response to a steady source that's just sitting there. So this is the analog to the ENSO situation, and so you get the familiar wave train into the northern hemisphere during winter. But the bottom left-hand panel is showing what happens. This is a snapshot for a forcing on the equator that's moving towards the west at 8 degrees per day, and this is a snapshot when that source is right at 180 west. And so you can see you also get a wave train into mid-latitudes. If anything, it's actually stronger than the steady case, but its structure is somewhat different. And the bottom right panel is what is the linear response if the source is moving towards the east at 8 degrees per day. And you can see that, again, you get a response, although it's much weaker and the structure is very much different. So we would like to see whether the response is also sensitive if one includes more dynamics into the situation. And one way to do that is shown on the next slide, which has to do with kind of a traditional the top of the panel here has to do with a traditional general circulation model approach in which one puts an anomalous heat source on the equator. And in this example, we've moved the heat source towards the east at 4 degrees per day. So this would be roughly at MJO kind of time scales. And this top diagram is showing on average what the response looks like. In this case, we're looking at the north-south wind component at 300 millibars. And so you can see that you do get a strong response into the winter hemisphere. But this is not a very efficient way to study this problem, because we had to for some of the statistics we wanted to look at, we had to do an ensemble, a 15,000 member ensemble, to get nice statistics in which we've moved the heat source towards the east, and we've had to go around the globe 15,000 times to get good statistics. So rather than use this rather cumbersome way to see how the response is a function of what the source is doing in the tropics, we've resorted to an idea from statistical physics namely the fluctuation dissipation theorem, which allows us to make a very good approximation to how the general circulation model will respond to a given heat source, but we can approximate it simply by a matrix, and that matrix we can calculate simply by looking at the natural fluctuations of the general circulation model. So we never actually have to insert a forcing function into the general circulation model. And you can see that in the bottom panel, this estimate from the fluctuation dissipation theorem is giving a very good approximation to how the full general circulation model runs. So from now on, I'm going to show you solutions from the fluctuation dissipation theorem, and they're designed to approximate the GCM. And so the next slide has to do with the sensitivity of the general circulation model to the heat source and the movement of the heat source. And so the three panels on the left are similar to the linear calculation, although here we're looking at the north-south wind component. And the top panel has to do with a source that's moving towards the west at 8 degrees per day. The central panel is when it's moving towards the east or it's steady, and the bottom panel is towards the east at 8 degrees per day. So you can see that now in this much more comprehensive situation, we're still getting strong sensitivity. We are able to get a mid-latitude response even if the source is moving, but the structure and the amplitude of that response changes a lot. So let's move on now to look at the, okay, I think I'd like to look at the right panel in this diagram too, which is summarizing the amplitude of these responses at latitude, as a function of latitude, which is the y-axis, and a
Grant,
function
I
of
just want to be sure I'm on the same slide as you. Are you on the storm track response to EQ heat source slide?
No, back please.
Response to moving equatorial heat source?
At the top of the page, it says dependence of V300 response amplitude on source speed.
Okay, sorry, I got ahead of you. Thanks.
Okay, so the right panel on this is just summarizing figures like on the left, and it's showing the amplitude as a function of latitude and as a function of the speed that the source is moving. So on the left part of the diagram, the source is moving towards the west very rapidly. In the center, it's steady. On the right, it's moving towards the east very rapidly. And so the point is that you're getting the strongest mid-latitude response when the source is either steady or moving somewhat towards the west. But the amplitude of the response is highly dependent on how fast the source is moving. Okay, now I'm going to go to the next diagram, which should be a single panel with a lot of blue on it.
We're right there with you.
Okay, so this diagram is now looking at the structure of the response, and on the x-axis is longitude. So this is looking at response as a function of longitude. This is in mid-latitudes of the northern hemisphere. And the y-axis has to do with how fast the source is moving. And in these solutions, we're assuming that the source is in the center. It's at 100. We're assuming that we're forcing this is when the forcing is at 180 west. And so the point is that depending upon the movement of the source, the structure of the mid-latitude response is very different, with much smaller scales in mid-latitudes if the source is moving towards the east. Now, of course, we'd also like to know whether this is affecting higher frequency transients, so the synoptic eddies, for example. And so the next diagram has to do with how the storm tracks are reacting to the response to a moving source in the tropics. So this has the same layout as the previous diagram, except now we're looking at a storm track quantity, namely the feedback produced by the transient eddies and their associated momentum fluxes, which we've represented as a stream function tendency. And so you can see here by this measure of storm track activity that depending upon how fast the source is moving, the amplitude and structure of the transient eddies and their feedbacks are also strongly dependent on how the source in the tropics is moving. So we still get, even if the source is moving, even if they were moving, say, at MJO speeds of 4 degrees per day towards the east, we're still getting a response in mid-latitudes, although it's somewhat weaker than it would be if we had a steady source like in the ENSO example. So the last diagram that I'm going to show you is the next one. And here we have applied our methodology, but instead of looking at the results from a general circulation model, we're looking at nature. So there's not actually enough data from nature to do a really excellent job with the fluctuation dissipation theorem, but we are able to get some rough estimates using fluctuation dissipation when we apply it to nature. And so that's what I wanted to show you on this last diagram. So the left panels are similar to what I showed you from the GCM, where we're looking at the response of the north-south wind component for heat sources on the in the tropics. The top panel, if the source is moving towards the west. The center panel is if it's steady, and the right is whether it's moving towards the east. And I just wanted to show you that the movement is actually making a big difference in the response. So let's just compare the steady and the eastward case. The eastward case is about moving at about the pace of an MJO. And look at the Gulf of Alaska. You can see that for the steady case, the responses are anomalous southerlies. But if the source is moving towards the east like an MJO, we get a anomalous northerlies. So there's enough difference sensitivity that it's making a big difference. And the right panel is showing how the amplitude depends on how fast the source is moving. And again, we see that the amplitude of the response in mid-latitudes is highly dependent on the speed of the source. So the last panel is just a summary to, again, point out that these transient Rossby wave events can have a big influence on the U.S. in particular. I showed you an example of how they're influencing the likelihood of heat waves, but mostly my message is that the structure, if these transient Rossby waves are stimulated from the tropics, their structure and amplitude is highly dependent on the movement of the source, how fast that source is moving. And the last thing I wanted to just reinforce is this idea that this fluctuation dissipation theorem seems to be a powerful tool for systematically looking at problems like this. Thanks.
Great. Thanks a lot, Grant. What I'm going to do is unmute the phone lines right now and see if we have any questions. Bear with me for a moment. All right. Are there any questions on the phone line for Grant?
Yeah. Hi, this is Dave Strauss. It's a very interesting talk. It seems, from what I gathered from your results, that you get more of a response with a westward propagating heat source than an eastward propagating heat source. Did you get the same impression?
Yeah, that's true. As long as it's not going too fast towards the west. Once you do get beyond a critical point where it starts to weaken. But yes, the maximum response is for slight or somewhat westward propagation. And the linear theory also suggests this.
All right, thank you.
Are there any other questions on the phone line? Okay, thanks a lot, Grant.
Sure.
Brian, are you on the phone?
Yeah, I'm here.
Okay, great. So what I'm going to do is switch control over to your computer right now. Just click the, oh, great.
Did it work?
It sure did. So whenever you're ready, take it away.
Okay, let me see if I can get this larger here. Okay, well, good afternoon, everyone. Today I'm going to talk a little bit about some work we've been doing here at Stony Brook University, a group of us here, looking at the historical and future prediction of extratropical cyclones here along eastern North America and the western Atlantic during the cool season. Obviously, there's a lot of societal impacts and influence with these type of events. In fact, just yesterday, Tokyo was hit with a big blizzard and hurricane force winds in the western Pacific with a major cyclone in that neck of the woods. But I'm going to be focusing here in the western Atlantic. and so forth. And what I'm going to be doing is, first, before we can look at the future, we have to have some confidence in these models for the historical past. So I'm going to be primarily focusing on the CMIP-5 models, looking at their cyclone density and intensity and deepening for the historical period 79 through 2004. And then we'll look at the future changes in these models and some of the possible reasons for these changes, which is actually work in progress. And then look at some other variables besides just pressure and cyclone things, such as precipitation and a little bit of wind and so forth. So for the study, for the cyclone analysis, we use the Climate Forecast System Reanalysis from NCEP 6-hourly to do the cyclone tracking, which I'll describe in a second. And I should mention we also use the ERA interim as a test, but it didn't seem to have much impact on our results, so I'm going to be focusing on the CFSR. We downloaded 15 models from CMIP-5 6-hourly for a historical period, and then also the RCP 8.5 scenario up into 2098. And it's a fair amount of data 6-hourly, so we only focused on this high emission scenario for this work so far. We actually started this project looking a little bit at the NRCAP, the North American Regional Climate Change Assessment Program, since it's run at relatively higher resolution, around 50-kilometer grid spacing, and I'll share a little bit of comparison of results with that as well. Just looking at this rough table here, this just lists the CMIP-5 members that we used, and I just want to point out those members that are in bold here are actually somewhat higher resolution, typically about 1.5 degrees or so or less. Because I will be making some comparisons between the higher resolution members and then some of the lower resolutions, which are greater than 2.5 degrees or so, as we go through the analysis here. For the cyclone tracking, we used Hodge's track approach. Actually, I gave a presentation about this about a year ago, although my voice was shot, and I don't think it was very comprehensible. But anyhow, I'm not going to have much time to go through the approach here today, except for outline the parameters, which was a wavelength of 600 to 10,000 kilometers, minimum lifetime of 24 hours, and moving distance of 1,000 kilometers. And these parameters were obtained basically through trial and error, because we did do a manual verification over a few cool seasons and determined that these parameters were within basically 5 to 10% error in terms of false alarm and probability of detection. I should mention we did try the Hodge's vorticity tracking, which is in the literature with some of his papers. We found, at least in this western Atlantic region, it tended to identify too many non-cyclone events, and which is why we focused primarily just on sea level pressure tracking for our analysis. Our domains of interest here are primarily this ECWA, this Western Atlantic, and then extending into Eastern North America region, this blue dashed line. But I'll also be showing you some results focusing on the East Coast, this ECL region for land and ECW for water regions, and so forth. I broke the future periods up into into 3 periods here, 3 30-year periods, early, middle, and late 21st century. For the NRCAP, we looked at several members here, both in a historical sense, forced either with NCEP or the GCMs, as well as some future GCMs. I'll just show you a snapshot from the historical as comparison here in a few minutes. But one issue with the NRCAP, our area on the East Coast is fairly close to the boundary of these regional models, which may be having some impacts and so forth. Okay, so let's jump into the cyclone track density here for the historical period to start with, focusing on the cyclone number per cool season per 2.5 degree latitude and longitude. The CFSR is in the upper left here. So let's look at that first. Basically, it shows nicely the storm track we're obviously dealing with here, just off the coast and extending northeastward with a maximum just east of Greenland. And another maximum near the Great Lakes and Hudson Bay region. On the upper right, we have actually the mean and spread of all 15 CMIP-5 members that we used in the study, and you can see it realistically predicts here this historical storm track here along the East Coast and Great Lakes and so forth. although in a mean sense, the amplitude is somewhat less than what we're seeing in the CFSR. What we did is separate these models into the 7 higher resolution members as members I showed in bold on the table, and then lower resolution members, which illustrates some of the benefits of high resolution, where you can see the higher resolution members have a somewhat more realistic storm track here in the Western Atlantic, extending a little bit more zonally. The lower resolution members tends to have that maximum too close to the coast, sort of hugging the coast more, which suggests it's not, these members aren't properly resolving the sea surface temperature gradients and so forth associated with the Gulf Stream and baroclinic development in that region. Looking at the NARCAP, just giving you a taste of what this system predicted here in a historical. The upper left is the CFSR again, just focusing in this black boxed region. And then the upper right is the NARCAP mean of several members forced with the NCEP reanalysis, and the lower left is forced with the GCMs in the historical period. And you can see the problem is that there's somewhat of a noticeable underprediction here in the NARCAP here along the coast here, either forced with NCEP and the GCM. And one could suggest here that the CMIP-5 seems to have a better structure even than these higher resolution NARCAPs. So this worried us looking at NARCAP in the future, which is why I'm going to be focusing on CMIP-5 here for the rest of my talk, given some of these underprediction problems shown here. So let's look at this, the intensity distribution for the CMIP-5 members, but first focusing on the lower resolution members. And we're looking at basically just the number of cyclones per cool season here, looking at the pressure here on the x-axis. The CFSR is in the black, and you can see it has a tail here, and these are the relatively deep cyclones in the Western Atlantic, which the lower resolution members cannot resolve, and so it's missing that tail, and it's also somewhat broader here on the weaker cyclones as well. If we look at the higher resolution members, there's actually a couple members that actually get this tail, and overall it's better, especially in terms of the CMIP-5 mean, where we actually have a pretty good prediction here for moderate to weaker cyclones for this. So both in terms of the intensity as well as the distribution, somewhat better here with the higher resolution members. We did do a quantitative verification. One more slide, I guess, before I show you that. I actually did the same intensity distribution here along the East Coast, which is closer here to North America, where there's less of a tail and the cyclones are not as mature, and you can see the CMIP-5 mean is actually closer to the CFSR here as we get closer to North America. And that's actually important because as we look in the future, we want to have a little bit more confidence in the CMIP-5 as we are closer to the East Coast, where it seems to be doing a little bit better. Okay, now a verification, a lot of numbers. I'm not going to go through all these numbers. Just to mention that we did various metrics here, track density correlations and track density absolute errors and central pressure correlations. And then we ranked the various members. These last 4 columns are actually the ranking. And then we have an overall ranking, which is basically the order of the models that you see here. And we're focusing on that Western Atlantic East Coast region. And you can see, the main point here is that 6 out of the 7 best models are the higher resolution members. But there are exceptions here. The MPI ESM is a relatively low resolution model near the, closer to the top here. And the MIROC-5 is a higher resolution model, which is closer to the bottom. So it's not all resolution. Obviously, there's other factors here, model physics and so forth, that can determine the ranking. But we focused a lot of the future results focusing on these best 7 models here, since we have the most confidence in them in terms of their ranking of these various metrics. And so when I present the results, I'll be focusing on this best 7 here going into the future. So let's look at the future here, looking first at the cyclone density change, basically these 3 future periods minus the historical. And we're looking at the relative change here in the cyclone density, and then the percentage change, which is the contours here in percent. Dots are actually locations where 6 out of the 7 best models have the same sign for the future change to give a little bit of significance to the results. And so you can see here in the Western Atlantic, as other studies have shown, there's a decrease in the storm the cyclone intensity here out over the Western Atlantic. But as we work our way towards the East Coast, there actually is less of a, basically near neutral or slightly positive change here in terms of cyclone density change here in the best 7. It also shows up in the mean of all the models as well, which I'm not showing you. And that basically increases slightly as we head into the future. If we focus on another metric, which is more of the deepening of these cyclones, the 6-hour deepening rate, and looking at the density of those those cyclones deepening more than 5 millibars here in 6 hours. The top 2 panels are the historical period, where we can see this 6-hour deepening rate greater than 5 millibars here, and the maximum just off the coast. And the CMIT-5 best 7 has a realistic structure here in the color fill with these deepening rates. Now what we're going to do is look at the future of these deepening rates, going into the 3 future periods. And as we head into the middle 21st century, we can have once again that weakening of deepening rates out over the Gulf Stream and Western Atlantic. But interestingly, just inland and along the East Coast, there's actually an increase of about 20 to 40% of more rapid deepening here in this region, and sort of maxing out here in the middle part of the 21st century, and then relaxing a little bit compared to the historical period in the latter 21st century. Just to look at this a little bit more carefully, we can just look at the number change of these 6-hour deepening rates going through these future periods. And the blue line is actually that middle 21st century where things kind of peak out here. The range of the models are shown by these bars, and you can see that there's basically on the order of 20% more cyclones deepening more than 4 to 8 millibars in 6 hours, which suggests these storms, there's a subset of these storms that are deepening more rapidly here. And we're focusing in here on this ECL region, basically that region just along the coast or just inland of the coast. We've been looking at some other parameters besides pressure here, and this is actually work in progress, but we downloaded a couple, 2 out of the 7 so far, best 7 models, looking at the 850 millibar wind change. And what it shows here is that for greater than 34 knots, there's about also about a 20 or 30% increase here for these 2 models in terms of increase in the number of events greater than 34 knots here at 850 millibars, which is another suggestion that that these cyclones are becoming more intense here heading into the future. A time series of the number of deep cyclones less than 980 millibars for this East Coast region also indicates this upward trend here in the best 7 models, where you can see by the middle 21st century it sort of peaks out, then it kind of flattens out a little bit. The various model solutions are shown here. Then also the CFSR, which doesn't have much of a time series here to show much of a trend yet. But this is that period here that's showing this increase into the middle 21st century. And we've been looking a little bit into this, although this is still work in progress, looking at some of the potential reasons for these changes. We've calculated things like ED growth rates between 850 and 500 millibars, and then jet changes at 250 millibars here. And I'm showing you some representative models here. In terms of the contours here, the dashed is actually the ED growth rate changes. So in terms of ED growth rate and the jet, the ED growth rate's actually becoming weaker as we go into the middle part of the 21st century, and the jet's actually slightly weaker. So that doesn't suggest that there should be more intense cyclones here along the East Coast. If we look at in the upper right, the surface temperature gradient changes, which is dashed, those are also negative, so there's slightly weaker temperature gradients here at low levels. The surface temperature difference between historical and the future is also shown here in the shading with the middle 21st century. And this is just the CCSM4 here in the upper right, just as a representative example. So in terms of the dry dynamics, looking at some of these parameters, they don't suggest much change here in terms of the cyclones. But one thing that is a fairly noticeable change is the precipitation and the percent change here, looking at basically the future middle 21st century and the historical, where there's basically a 20 or 30% change here along the East Coast, which leads us to hypothesize that the diabatic heating or latent heating from this precipitation increase may be an important influence in helping to deepen these cyclones more as heading into the future. But this is work in progress, and experiments need to be done to look at that more carefully. The last thing I want to show you here is just the precipitation change in general for the CMIT-5 models. And we actually have 14 models, I believe, for this. This is actually the climatology during the 5 cool season months in the upper left. But we did some verification within this black box region, which is basically the northeast U.S., using the unified precipitation analysis over land, basically. The unified is shown in the dashed line here, where we're looking at basically the number of days for certain precipitation thresholds, and the various models are shown. And you can see a very large spread with these models, and there is some overprediction with a cluster of models overpredicting by about 10–20% or so here, with the black dashed, with the black solid being the CMIT-5 mean. So keeping that in mind, we did look at the future of the latter 21st century minus historical for these precipitation changes over the basically eastern North America and northeast, and it's about, in terms of the solid contours of the percent change, it's about a 25% increase here over the northeast U.S. in terms of precipitation amount. But more importantly, in terms of the distribution of precipitation, daily precipitation, which is in the lower right, these lines that are heading up here are heading into the middle and late 21st century, where there's about 2 to 4 times more events with more than 20 millimeters per day as we head into the latter part of the 21st century, suggesting that there's more basically heavy precipitation events here in that particular region. So in summary here, the CMIT-5's model seem to realistically predict the cyclone distribution in the historical period, although there's some underprediction in terms of the number and intensity of these cyclones. The higher resolution does seem to help with the CMIT-5 in terms of better simulating this density and intensity, but they also underpredict, some of these models also underpredict these intense events. The cyclone numbers decrease over the western Atlantic, but there seems to be a more rapid deepening storms just inland of the East Coast by the mid-21st century, as well as more heavy frequent precipitation events. And the work we're currently doing is trying to understand a little bit more about what's going on with this response. They're just looking at some indices like ED growth rate and changes in the jet. There doesn't seem to be much positive impacts there for cyclones. The biggest thing we can see just looking at the CMIT-5 model output directly is just a lot more precipitation and potential for diabatic heating. So with that, I'll close and take any questions.
Great, thanks a lot, Brian. Are there any questions on the phone line or here in the room for Brian?
Hi, this is Arita. Hi.
Hello.
You mentioned that you looked at the NOAA experiment to get similar results out of that.
I'm not sure if I heard your question. Did you ask about the NARCAP?
Yes.
Yeah, we did look at the NARCAP for the historical, like what I showed you, and various other parameters, and also the future. And I can tell you that NARCAP does not have as much of this response that I'm showing you along the East Coast. So it's much weaker in the NARCAP model.
Okay, thanks.
But my concern was, I'm really worried about the boundary and the NARCAP so close to the East Coast, and we've been having similar issues with running WRF and figuring out the best setup and downstream boundary. There seems to be a lot of sensitivity with boundary conditions and these predictions.
Mm-hmm. I was wondering whether you know whether the the high resolution time slice experiments are going to be available soon, and whether you're planning to use any of those.
I'm not sure when, in terms of available. I mean, we're doing our own downscaling work here, but yeah, I'm not sure about those time slice experiments.
Are there any other questions for Brian on the phone line? Or any questions for any of the speakers? Okay, well, I'd like to thank all of the speakers. It's a really excellent webinar today. Very interesting talks. Thank you all for participating. Thanks everybody for calling in. Our next webinar is going to be on February 12th on the topic of drought monitoring and understanding. We have 4 speakers on the 12th. We're going to hear from Amir Agakuchak of University of California at Irvine, Chris Hain from NOAA NESDIS, Krista Peters-Ledard from NASA Goddard, and Andy Wood from the NOAA Northwest River Forecast Center. So thanks again, everyone, for joining. Thank you to our speakers, and I hope that you'll be back next month.
Thank you.